Hi guys, in this video we are going to learn how to perform the extract minimum or the delete minimum operation in Fibonacci heaps. So in the previous video we learned many operations in Fibonacci heaps such as create heap, insert an element in a heap, how to find the union of two Fibonacci heaps and how to find the minimum element in a Fibonacci heap. And we also calculated the amortized time complexities for all those operations. Even in case of the delete minimum operation, after explaining you this operation step by step, at the end of this video, we will also try to calculate the amortized time complexity for this operation extract minimum. So let us start. So in this extract minimum operation, we actually delete the minimum element of this entire Fibonacci heap. So which is the minimum element of this entire Fibonacci heap? It's 4. And there is always a pointer, this minimum of h, that is pointing at the minimum element of a Fibonacci heap. So every time this pointer is storing the value of the minimum element, right? So we need to delete this element. So in the first step, we will actually delete the minimum node, right? So in the first step, we will delete the minimum node. That means we will delete this 4, right? But after deleting this 4 also actually has a lot of descendants, right? The tree that was rooted at 4 has a lot of descendants. So what to do about these descendants? So in the second step, what we actually do is that we take this root list of the descendants. So this basically, so these are the siblings, right? So we take this root list 23, 29 and 59 and we attach them to the Fibonacci heap. So we take this root list of this descendant nodes, we take this root list and we attach them to the Fibonacci heap. So I'll do it over here. So what we do in the second step? So in the second step, we actually join this root list to this Fibonacci heap, to the root list of the original Fibonacci heap. So this is the root list, this 24, 14 and 64 are in the root list of the original Fibonacci heap. So we join this root list to this root list. So let me do it over here. So as you can see over here, what I have done is that this root list of the descendant nodes of the deleted minimum element, I have joined it in the original root list. This original root list where the rest of the roots are there for the rest of the trees of the Fibonacci heap, right? So I have joined it in this way. That was the second step, right? So now as you can see over here, I have got many trees after performing the second step, and let me see the degree of all these trees. So the degree of this tree is 1 because its root has 1 child. The degree of this tree is 2 because its root has 2 children. The degree of this is 0 because the root has 0 child. 1, 0, 1. Okay. So as you can see, here I am having many trees and there are trees that are having the same degree as well. Like you can see over here I have got 3 trees with degree as 1, right? And one more thing that if you can notice is that when we deleted the minimum element, 4 was the minimum element. When we deleted it as per our operation of delete minimum, right now we don't know which is the minimum element. But as you know, this minimum of h has to point at the minimum element of this Fibonacci heap. But it doesn't know which is the minimum element. So what it can do is that it can traverse this entire root list, because as we know, in case of a Fibonacci heap, each and every tree is following the heap ordering property. So its minimum element, so the minimum element suppose for this tree will be at its root. So this minimum of h has to look at all the elements of this root list, that is 24, 14, 64, 23, 29 and 59, in order to find the new minimum element so that it can point to that element, right? But while traversing this entire root list, one more thing that we will do is that we will ensure that when we finish this traversal, we only have trees with unique degrees. That means we should have only one tree with degree 0, we should have only one tree with degree 1, we should have only one tree with degree 5, we should have only one tree with degree 3. There should not be more than one tree of the same degree like it is happening over here, right? So we will do these two things. While traversing from left to right, we will try to find out the new minimum out of all these roots, and at the same time we will try to merge those trees that have same degree so that we don't have more than one tree with the same degree, right? So we will do two things in our third step. This will be our third step, that we will move from left to right in the root list and we will find the new minimum. So that is very easy, finding the minimum element out of all these elements. But we will see that how we will merge trees with same degree. So now merging trees with same degree is not as easy over here as it was in case of binomial heaps. So you can refer to my video of merging two binomial heaps. You will find it in the side button. Because the problem over here is that in case of binomial heaps, because we were merging two binomial heaps, so in that case, the B0 and the B0 used to come together. It wouldn't happen that there was a B0 here, the B2 here, B1 here, and then a B0. In that case, we would have to merge this B0 and B0. But that was not the case in binomial heap. It was not possible that such kind of order we will face. But in case of Fibonacci heap, we can face such a thing, right? Because there is no particular order in which these trees have to be arranged. Like as you can see over here, the 0 degree tree, right? The 0 degree node has to be merged with this 0 degree node. Am I right? How will this node know that there is actually a 0 degree node behind me? In order to keep a track of this, we actually need some kind of storage, right? So we store this information in what is called as an auxiliary array. Auxiliary array will store pointers, okay? So basically auxiliary array will be an array of the size of dn, okay? So dn is actually basically equal to the maximum degree of any node in the tree, right? So dn is equal to maximum degree of any node in the tree. Later on, we will actually dive deeper into why we have chosen this size as dn. So dn is actually equal to maximum degree of any node in Fibonacci heap, right? We can call this as A0, A1, A2, A3, A4, right? In the same way. So this is an array of pointers, okay? So what it will store? So initially, all these will be null, okay? But whenever, suppose we find a root with degree 2, so this A2 will point at that node, okay? Suppose we find a root with degree 0, so A0 will point at that node, okay? So this auxiliary array will work in that way. Let us see it's working by doing this third step. So we will understand it's working much better when we do this third step. We will actually start a kind of a current pointer from this place, okay, from the left side. And we found a root with degree 1. So when we find a node with degree 1, then we will go to A1, okay. We go to this index and we see that it is null. So originally the value stored in A1 is null. That means until now, no nodes were encountered that had degree 1. So we will actually change this from null to point it at that root which had degree 1. So what was that root? That root was 24, right? So root 24 had degree 1. Then my current pointer will move forward, okay? It will move to this position, okay? Now what will happen is that it will check, okay, this node has degree 2. So it will go to A2, okay? It will see that in A2, the value is null. So it will make it point to that node which has degree 2. So what is that node? That node is 14, right? So this A2 will be pointing at 14. Okay, it will be pointing at the root 14. So now what will happen is that this current pointer will move again, it will move forward. It will move over here. It will come at 64. It will see that this node or this root has degree 0. So it will check at A0. So A0 is null. That implies that until now, no root was encountered that had degree 0. So now because a root is encountered that has degree 0, it will point at that node, okay, and that node's value is 64. Why are we doing that? So that later on when we encounter another node with degree 0 and we check at A0, so we will find, okay, there was actually before another node with degree 0 that was 64, so we merge both these nodes. Okay, then this current pointer moves from 64 to 23. Okay, so when it moves to 23 and it checks, the degree of this root is 1. Okay, so it will go to A1, okay, and there it will check that actually A1 is pointing at the root 24. So basically there was another root with degree 1. So this root and that root at which our current pointer is pointing, these two roots or these two trees have to be merged, right? So which are these two trees? 24 where A1 is pointing and where our current pointer is pointing, that is 23. So this 24 and this 23, right? This 24 and this 23. So we have to merge this tree and this tree, right? But while merging, we also need to take care of the heap ordering property. So which will be the root of the merged tree? Will it be 24 or 23? It will be the minimum element. That means 23 will be the root of the merged tree that will be of degree 2. Why? Because we are joining two trees with degree 1, right? So 23 will actually be the root of the merged tree, and here we will have 24 and 32, right? So this will actually come from here to there, and the final degree will change of this thing from 1 to 2, right? And our current pointer is still over here, right? And now as there are no more elements of degree 1 that we have encountered until now, so A1 will again become null, right? Because there are no more roots that we have encountered until now of degree 1, because those two which were present earlier have been merged to form a tree with degree 2, right? Now as it has merged and its degree has updated from 1 to 2, so now it will check at A2. Why? Because now it wants to check that is there actually any other tree that we have encountered until now of degree 2. So it will check at A2. It will see that A2 is not null. It is holding the address of 14. So yes, it was right. As you can see, this A2 is basically pointing over here, right? So now there are two trees or two roots with degree 2. So we cannot have two trees with degree 2. So we need to merge them, right? So we will be merging this tree and this tree at their roots, right? So I'll merge them over there and write the result. So now as you can see, I've merged this tree of degree 2 and this tree of degree 2 to form this tree of degree 3. And I've taken 14 as the root because it is the minimum element of both these roots, 14 and 23, right? So my current pointer is still pointing over here, and the degree here is updated as 3, and here the degree is 0, 0, 1, right? The root of this tree has one child. Okay, so now let's move further. First of all, before moving further, it will check at A3. Is there any tree encountered until now with degree 3? So it will see that the value at A3 is null, right? So the value at A3 is null. So it will make A3 point at 14, right? Because this is actually a tree with which has a root of degree 3. At the same time, A2 will not be pointing at 14 because now the 14's degree has changed from 2 to 3, right? And this A0 is actually pointing at 64. So let us draw it in this way. This A0 is pointing at 64. Okay. So now this current pointer, it moves forward, right? Now it checks that 29 has degree 0. So it will check at A0. So we see here that A0 is not null. There is another element with degree 0. So we join both these nodes with degree 0, that is 64 and 29. So which will be the root? 29 will be the root because it is the minimum element out of these two, right? And we have to follow the heap ordering property. I add 64 over here and the degree of this tree changes from 0 to 1. Okay? So now this A0 will again be null, right? And my A2 is also null. And my A1 will be updated from null to point at this 29 because the degree of this node changed from 0 to 1 just now because of this merge happening between 29 and 64. So my A1 will change from null to point at this element, right? So now my current pointer will move from 29 to 59, okay? So it will check at A1 because it has degree 1 that is there any other node that was encountered before that has degree 1. So here it will see there is a node and A1 is pointing to that node which is 29. So now these two trees will be merged which have the same degree, right? And 29 will be the root because it is smaller than 59, right? So now I have merged these two trees and the degree changes from 1 to 2. A1 will no more point over here, it will be null, whereas A2 will change from null to pointing at this node which has degree 2. So now as you can see, we have merged all the nodes, and because this is a circular doubly linked list, my current pointer will come back at 14 and it will see at A3. So A3 is storing 14, right? A3 is already storing 14. That's the same value which current is storing. So whenever current is equal to AI, right? So whenever both these pointers are pointing at the same location, we have to exit. Okay, that means we are done with the extract minimum operation. We have deleted the minimum element. And now you might be wondering that we didn't find the new minimum element. But while we were performing this entire operation, we were also actually trying to find the minimum element, and our minimum element now points over here, right? Our minimum of h will point at 14 because it is the minimum element out of these two. So this was the extract minimum operation. Now let's try to find out the time complexity for this operation. So for finding out the time complexity, we are going to use amortized analysis, and in amortized analysis we will use the potential method, right? So I have already explained the potential method of amortized analysis in my initial videos of this playlist. I'll provide the link to that video in the side button if you want to refer them. So we have already discussed the potential function of Fibonacci heaps in the previous video, that is th plus 2 into m of h, right? And what is th over here? So th is number of trees in the Fibonacci heap and mh is the number of marked nodes in the Fibonacci heap, right? And the formula for the amortized time complexity is ci cap, or the amortized cost, is equal to ci, that is actual cost plus change in potential, right? So now let us assume that the initial potential is th plus 2mh, right? This is the initial potential of our Fibonacci heap before we perform the extract minimum or the delete minimum operation, right? And what about the final potential? So just tell me one thing, that after we perform the extract minimum operation, are the number of trees changing in the Fibonacci heap? Yes, they are changing, because what we are doing in the second step is that in the root list, we are joining deleted nodes descendants, right? So we are joining in extra trees over there. And then finally we are actually merging the trees with the same degree, but let us assume that no trees are merged. No trees are merged, or all the trees have unique degrees. So now the next question that should arise in your mind is that what can be the maximum number of children of any node in a Fibonacci heap? So that is actually represented by d of n, that is the maximum degree of any node in a Fibonacci heap, right? And this is for a Fibonacci heap that has n nodes, right? So this can be the maximum degree. So that means these many extra trees can actually be added into your original root list, right? So the number of trees can increase from th to th plus d of n. But we should also do a -1. Why? Because the node that you have deleted, actually that tree has vanished, right? We are making new trees out of all the descendants. So the deleted root, that tree which is actually starting from that tree which was actually rooted at the deleted node, that tree is deleted. So we do a -1 over here. So this can be the final potential. But in the third step, we actually perform this operation where we actually merge the trees with the same degree. So this operation is also known as the consolidation operation, right? This is actually the consolidation operation, this third step. So in this, after this operation, the maximum number of trees that can remain is dn plus 1. So the number of trees after the second step were these, right? But the number of trees after the third step will be these, right? But what about the potential? So the potential, so in the potential, it will be d of n plus 1 plus 2 into mh, because there is no change in the number of marked nodes, right? Until and unless the deleted node was a marked node, but that will make a minor change of suppose -1. No, nothing more than that, right? So this will be the final potential. This will be our final potential. And what about our actual cost? So the first step will actually take order of 1, just deleting the minimum node. The second step where we join the root list of deleted nodes descendants. So when we are actually joining that list to our original root list, so when we are actually joining the deleted nodes descendants to the original root list, at that time we are actually increasing the number of, after that we are actually traversing the entire list, right? So the number of nodes in the entire list will be our actual cost. So what will be that value? T of h, or the original number of trees in our list, plus d of n, or you can say the maximum degree of the deleted node, that is d of n in a Fibonacci heap, right? So now if I find out ci cap, so that is equal to t of h plus d of n, that is our actual cost. So this is my actual cost plus my final potential, because the change in potential is final potential minus initial potential. So my final potential is this. So this is my final potential minus, what is my initial potential? T of h plus 2 into m of h, right? So now here this 2 into m of h will get cut, and this th will also get cut, and what will remain is 2 into d of n plus 1, or you can also call it as order of dn, right? And the maximum degree of any node in a Fibonacci heap, or what we call as d of n, is actually equal to log to the base n floor, right? So this thing that is order of d of n, we can actually write it as order of log n in a Fibonacci heap which has n nodes. So the time complexity of the extract minimum operation comes out to be order of log n, right? So that's all for this operation of extract minimum, in which we saw how to do these 3 steps and we calculated the amortized time complexity for this operation. In the next video, we will see that how do we perform the decrease key operation and the delete operation in Fibonacci heaps. That's all from this video.